So now we've learned a little bit about the relationship between frequency and wavelength and the speed of light. What's the frequency of a radio station if it transmits at 300 megahertz? Or sorry, what's the wavelength of the light if it transmits at 300 megahertz?
The frequency is... No, so the wavelength is what we don't know?
That's right. Wavelength is what we don't know. Now, do you remember what the relationship between the wavelength, the frequency, and the speed of light was?
Speed of light. I don't remember that equation.
Okay, let's try to use the units to help us figure out. What does this one stand for?
Did you say wavelength?
Yeah, so what are the units for wavelength?
Length, meters.
Very good. Do you remember the units for frequency?
That's how many times per second?
That's right, so it's per second. All right, and what are the units for the speed of light?
Meters per second.
Very good, meters per second. So can you see what has to happen in terms of the units?
Yeah, I see it now. So wavelength times frequency equals speed of light.
Okay, very good. So wavelength times frequency, these units here times each other will equal the units of speed of light. Okay, good. So we just need to get the correct units, and then we'll be able to find out what the frequency, or sorry, what the wavelength is for this frequency. So if the frequency is 300 megahertz, do you remember how many mega is?
Oh, that's a million.
That's right. Good. So 300, and I'm going to make it 300 million hertz, so that's per second. Multiply that by our wavelength, and that's our unknown. And oops, not multiply it by our wavelength, and that equals the speed of light, which is 3.8 times 10 to the 8th meters per second.
How did you know that?
Oh, I remembered that. I should have told you that. But the speed of light is always, it's that constant, okay? And it'll always be provided for you on questions where you need it. Okay, so just 8.8 times 10 to the 8th divided by 3 times 10 to the, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8. So it's 3 times 10, 3.0 times 10 to the 8th. Divided by 3 times 10 to the 8th. So this is essentially going to be 1 meter long. Okay, or 0.99 if you use the speed of light of 2.99 times 10 to the 8th. Oops, that needs to be times 10 to the 8th. Okay, very good. So, a long time ago, people began to realize that if you took a piece of material, specifically a metal, if I take a metal, all right, and I try to draw a current off of that metal from a wire, that means I'm trying to pull electrons off of that piece of metal with a wire, okay? So electrons can't just jump off of the metal because they can't just be leaving that metal surface. However, what was discovered was, I mean, if you pull a hard enough voltage, yeah, you can begin to oxidize that metal. But what was discovered is that if you take electromagnetic energy in the form of different wavelengths of light, and you shine it on this piece of metal, those wavelengths of electromagnetic energy can induce the electrons to jump off of the metal. Almost like these wavelengths are little meteors or packets that are hitting that surface and knocking those electrons off and allowing the current to flow. All right? And what they discovered was that this energy, the energy necessary to make electrons jump off of the metal here, was related to the frequency, or the wavelength and the frequency, right? Because they're both related to some way, of our electromagnetic energy that's hitting that surface. Okay? So, they found that there was a certain threshold of wavelength necessary, or frequency necessary. And once you reach that frequency, then all the electrons would begin to jump off. It wasn't related to intensity like people thought it would be. So they thought that, if you shined a little bit of a wavelength and no electrons jumped off, if you just shined a lot of that same wavelength, then electrons would begin to jump off. That would be more intensity, but that wasn't the case. You needed to reach a certain threshold of energy. And this differed for different metals. So if you had gold, silver, zinc, whatever your metal was, they would hold electrons differently. And so what they began to see is that electrons were held differently on that surface, and that light could actually be used to make the electrons jump off. And this finding began to kind of confuse people about what their model of the atom was. So it began us to think about how the energy of the light could be related to a constant here, which is called Planck's constant. And this constant came from experimentation with this photoelectric effect. And what we found was that 6.626 times 10 to the minus 34 joule seconds will be released per photon. Okay? Or in other words, you could take that constant, Planck's constant, which has units of joule seconds per photon of energy, or photon of electromagnetic energy, and then multiply it by 1 over seconds, which is the frequency, and that told you the energy of that given photon, or that given wavelength, okay? Given frequency. So, to get the energy in joules of a given electromagnetic frequency, you would multiply the frequency times Planck's constant. Okay? Planck's constant will always be provided for you, and it'll usually just be in joule seconds, not per photon. But from the units there, again, you can see that I have to multiply this joule seconds times the frequency to get the seconds to cancel out, so that I'll be left with joules of energy. Okay? So, looking at ultraviolet light, 320 nanometers, compared to red light, 700 nanometers, we can find their energies to identify why 320 is more energetic. We can take the wavelengths, 6 times 10 to the minus 9th meters, right? 3 times 10 to the minus 9th meters here. Oh, this should say, 7 times 10 to the minus 9th. We're using 700 nanometers. And then 320 here nanometers. And we can take those wavelengths and solve for the frequency. So to solve for the frequency again, 3.2, 320 nanometers is 3.2 times 10 to the minus 9th meters. Now I need it in meters. Why do I need it in meters?
What are you doing?
I'm taking the wavelength here, and I'm trying to find the energy, right? I'm trying to find the energy. But before I can do that, I need to find out what the frequency is, right? The frequency, all I have to do with the frequency is multiply it by Planck's constant, and I get the energy. But if I have the wavelength, how can I get the frequency?
Oh, okay. So the wavelength is equal to the... Well, you multiply the wavelength times the frequency and you get the speed of light.
Very good. So if I have the wavelength, I can find the frequency. Speed of light divided by the wavelength will give me the frequency. And then I multiply the frequency times the Planck's constant to give me the energy. Okay, so 3.2 times 10 to the 9th meters, that's my 320 nanometers. I converted it to meters because I know that the speed of light is 3 times 10 to the 8th meters per second, right? And so then I can solve for my frequency in units of 1/seconds. Okay, very good. So do that in my calculator. 3 times 10 to the 8th divided by 3 times 10 to the minus 9th. 3 times 10 to the 8th divided by 3.2 times 10 to the minus 9. That's 9.3 times 10 to the 16th, 9.37, 9.4 times 10 to the 16th. And that is my frequency. So my frequency equals 9.38 times 10 to the 16th. That's my frequency. And now what do I do with that?
After you get the frequency, you want the energy, you just have to multiply it by Planck's constant.
That's right. So let's go back here and get Planck's constant, 6.63 times 10 to the minus 34. So 6.63 times 10 to the minus 34. So we got 6.63 times 10 to the minus 34. Whoops, did I do that wrong? Oh, there we go. I just didn't push the multiplication button. So I got 6.2 times 10 to the minus 17th. Okay, so again, I took the 3.2 times 10 to the minus 9th. That's where I got that. Those were my meters. That's the wavelength. Wavelength times the frequency equals the speed of light. So to isolate the frequency, speed of light divided by the wavelength. And then after I got the frequency, I could just multiply it by Planck's constant to get the energy. Okay, very good. So what is the correct energy associated with the photon of light that has a wavelength of 450 nanometers? Okay, I'm going to let you guys try to work on this one, and then Fred will do it for us after we get back. So push pause and take a second to do it. Okay, did he do it? Good. So what do you think, Fred?
450 nanometers. To get the joules, the energy, we need to get the frequency, right? Because the frequency times that constant. What was that constant?
Planck's constant. Yeah. Frequency times Planck's constant. What was that?
That's how you get the energy.
Very good. So how do we get the frequency?
Well, the wavelength times the frequency equals the speed of light.
All right. The speed of light equals the wavelength times the frequency. And what is the wave's length here?
Well, it's 450 nanometers, but we want it in meters because the speed of light is 3 times 10 to the 8th.
Meters per second?
Yeah.
Okay. So our wavelength, what is our wavelength?
4.5 times 10 to the minus 9, right?
That's right. 4.5 times 10 to the minus 9. Okay. Very good. And then 3 times 10 to the 8th divided by 4.5 times 10 to the minus 9. That should give us our frequency times our Planck's constant, 6.63 times 10 to the minus 34 times our frequency, right? That should give us our energy. Okay, very good. Make sure that you can work your calculator. These are larger numbers or very small numbers, but scientific notation. Make sure you can work your calculator to get these values because that'll be critical in answering questions. All right.